Hello everyone, my name is Gurnoor Singh and this is my video demonstration for SIT315 in which I'm going to explain complex computing, complex distributed computing. And this task basically involved me to create two programs. First one was using MPI only. And by using this MPI only program, I had to make a parallel program for quicksort algorithm. And I have done here that as well. And then the part two was comprised of creating a Yeah, and part two actually involved creating MPI plus OpenCL program in order to parallelize the sequential program that I had created in part two of complex computing. So over here, I've got my first program, and in this one, I initialized whatever libraries that were required. That was my MPA program library. Then we have the vector as well as the chrono, which is essential for measuring time. And as we move further in this program, we can see that there are some things which are basics, and that's why very similar to the sequential program that I created in previous module. And in this one, first, obviously, the partition function, that is an important part of quicksort algorithm, as what it does is basically divides the algorithm into the given actual data set into two parts by choosing a point in between the data set. Afterwards, we have the quicksort, which actually then sorts each local chunk using this quicksort algorithm again, because we know that quicksort is a recursive algorithm. So afterwards, we have a main function here in which we initialize our MPI initials here. And you guys can see that I have given a section for the user to enter the input of the data. And so, yeah, reading size input from command line. And by default, the input size is 1 million. And yeah, that's the then over here, I have initialized my root process because through this root process, the initial processing is going to start, and we are going to get our output. And yeah, so after we initialize a data set here, it goes to the root, and afterwards it's scattered using MPI scatter function over here. And then quicksort gets these local chunks afterwards when this uh, data set is scattered, it's sent to quicksort. And then quicksort function, what it does is basically sorts these data sets locally, as you guys can see here by this function. And afterwards, the whole data set is sorted. Given to the MPI gather function over here to gather all the results. And MPI barrier is used in order to stop the high resolution clock that we have via the chrono library. And afterwards, the results are printed using this cout function over here. So what I will just do is I've already compiled this program. I'll just run this one using, I guess, 8 processors, let's say. MPI run minus NP8, and actually I should go minus NP4. Yeah, run minus NP4. The file name is complex, sorry, / complex computing 1. And so my input size should be, I guess, 1 million or 500,000 is good. 1, 2, 3. So 1, 2, 3, 4, 5. So yeah. So running MPI quicksort with n is equal to 5004 processes. The result I get is around 27 milliseconds, which is quite good, I guess. And then let's move on to a second program and compare how it works. I'll delete this terminal. Complex computing 2, that's the second thing we have here. And what, as you guys can see, it's much more longer than the previous program that we had. And in this one, we are using MPI with OpenCL, which is something I will explain during this program only. So we have the kernel specified here. And then you guys can see we move forward towards my MPI initializations. And that's the function I have here for getting the input from the user for the problem size. By default, again, that's 1 million, but we will specify when we enter through the terminal. And then we have a root processor here, which creates all the data. Afterwards, we have the MPI scatter function. Again, as we know, it basically scatters the given data locally, and then each local is scattered function. Sorry, a chunk is then gathered back using the MPI gather function here, and then again displayed. One essential thing and the difference that this program has that these distributed chunks are basically sorted locally with help of GPU. So instead of CPU processing, we are using GPU processing here, which is sort of much faster and gives us more efficiency. So what I will just try here is, yeah, terminal, terminal. I should run this one. Yeah, C++ complex computing to .cpp minus L CL is 2 minus 4. And then you have, yeah, compiled. And to run this one, you have MPI run minus NP4 slash complex computing. Let's run this one and observe what do we get here. So yeah, 72 milliseconds this time. And the reason being for that is essentially what should happen is that uh, our program should deliver us a output which is much more less than the only MPI program, since it's using GPU, which is much more faster. But an essential component of processing here is that when we are dividing a given data set into more number of processes, a communication overhead takes place as well. Over here, it's 72 milliseconds, which is quite less than around 40 that we got earlier. And that is because each data chunk is divided into 4 processes, but those 4 processes are again had to be combined again to deliver us the output. And that's why the synchronization cost and the communication cost that takes place during processing overrides the advantage that we get through GPU. So that's why the output that we have here is 72 milliseconds, and this is much more prominent about for other observations as well, since I've tried this for much more number of other data sets as well. So overall, I can say that this was the concluding part of my program here, that not every time when we increase the number of processes or processing hardware or anything, we will get a much more efficient timing. Sometimes I guess simpler is much more better, and this output actually describes the whole point that I'm trying to make here. So yeah, this is the video demonstration here, and yeah, thank you.